Hello, this is Gabriel Palmer, and today I'm going to talk about the Composite Component-Based Operating System, which is an OS that we've been working on for about 15 years. I'm going to be talking about a lot of research that we've done at GW, and I've done a lot of this work with the amazing researchers listed here. A lot of our work on Composite has been motivated by the idea that there's a convergence in requirements between systems that have historically been quite disparate. So we have embedded systems that have focused almost entirely on things like predictability, simplicity, size, weight, and power, and cost, and all of these types of factors. But then on the complete other end of the spectrum, we have these massive data centers that have multi-tenant clouds. And these focus inherently on performance. We want to push as many client requests through them as possible. Things like isolation, especially multi-tenant isolation, and elasticity, the ability to scale up and down. And what we've been noticing is that there's been an interesting convergence between these two things, in that we have the predictability requirements of embedded systems being ported over to the cloud. People care mostly now about things like tail latency. We also have the performance constraints of the cloud percolating down to embedded systems as we start to consolidate more and more things onto our small systems, right? Autonomous vehicles are a very good example of this. And we care increasingly about isolation and security on embedded systems. In some cases, full-on multi-tenant isolation. Now, the problem with this is that when we start having all three of these things in the same system, be they in embedded systems or be they in the cloud, we have a very difficult system design optimization. When we're implementing our operating system, we need to say, I need strong isolation, but I also want performance. But these are contradictory to each other in many cases, because isolation requires protection domains, performance requires efficiency, right? Requires not switching between protection domains frequently. Predictability and performance are often at odds simply because when we want predictable performance, we want to be able to put bounds on how long it takes to respond to different impulses. But to do so often requires that we make optimizations that make performance much more difficult. Isolation and predictability are often frequently at odds as well, for similar reasons to why isolation and performance are not often seen in the same system. So we have this really interesting type of a design space, and a lot of what we've been doing is researching how we can effectively design an operating system that works very well for each of these domains and each of these different optimizations, but can also satisfy the requirements of all of them. So as you can see here, we're essentially trying to provide a foundation that provides performance isolation and predictability for a number of interesting domains. So how do we do this? From the very start, Composite has been focused on the idea of being a component-based operating system. And the idea is that it is very difficult to implement one version of functionality that will meet all of these requirements. So what we really want instead is the ability to customize the functionality of the system for the requirements of the overall system and its goals. So what is a component? I think most people who are at this conference understand what it is, but it's also one of those things that means different things to different people, so I just want to be explicit here. When we think about components, we think about some code and the associated data executing at user level, and we call this the functionality. That functionality is typically an implementation of very specific APIs, where each of these APIs that gets exported for other components to use consists of a number of functions that have some sort of a, supposed contract, some sort of a required functionality provided by the component itself. And then, of course, that component cannot necessarily implement everything itself that it needs from the system, so it has a number of explicit dependencies on APIs that should be provided by other components. So when we look at components in this way, they are a unit of reuse in the system, and because they're implemented at user level and in our system in separate protection domains, they're also a unit of isolation. Now, a goal that we typically have in these systems is to minimize the functionality provided within each of these components that's necessary for implementing the APIs that it exports. This is simply another way of saying that when you're implementing your components, you want to implement them in accordance with the principle of least privilege, right? You only want them to require the implementation that's minimally necessary for what they're trying to implement. And this minimizes the number of dependencies that they have on other parts of the system. And if we do this, you actually end up with a fair number of components in the system, and this provides stronger fine-grained isolation than you see in a lot of different systems. One of the benefits of this is that we can start thinking about the implementation of systems as just the composition of components together. So here you see a system where we have a number of system services, each exporting, in this very trivial example, a interface. Some of them require other interfaces from other components. We have applications at the top that rely on some functionality, etc. So we have composed a system out of components, so design has moved to that level, right? And now the scope of things like security compromises, of faults within some of these service components, and the unpredictability within the system is limited by design. So for instance, when we think about App 1 and App 3, it might be the case that App 3 is relatively trusted and relatively simple. All that it's doing is talking to some device over I2C, using a channel to pass some data maybe to App 1 that talks over the network, right? App 1 might be relatively complicated, App 3 maybe not so much. So we'd really like the facets of the system that are required by App 3 to hopefully be somewhat isolated from the potential compromises or faults of App 1. And we can see that we can simply look at the intersection of the two sets of dependencies for these applications to see which ones need to be in the trusted computing base. So I think this is probably kind of secondhand to a lot of people here, relatively obvious, but I think it's worth saying that this ability to design the system out of components is in some sense a little bit of a superpower. The problem is, how do you actually design a system in which you can define all of the policies that are important for these goals of performance, predictability, etc., in components at user level, right? This becomes very difficult, and it actually harkens back to what Lika gave as advice for microkernel design in '95, and that is that a concept can be tolerated inside of the microkernel only if moving it outside of the kernel, i.e. permitting competing implementations, for example, different components, would prevent the implementation of the system's required functionality, right? We should only put something in the kernel if it has to be there to implement the functionality of the system, right? So we want to be able to implement all of these things in components. That begs the question, what needs to be in the kernel? And most microkernels try to adhere to this type of advice, but they all kind of need to make trade-offs in different places. Composite, in some sense, is a research lab that allows us to really try to push this far. So Composite tries to push this to the extreme in the sense that we want to have component-defined, user-level defined things like scheduling, whereby there is no scheduler within the kernel. All of that is defined in some sort of a user-level component. The parallel scalability properties of the system should also be defined, and if limited, they should be limited by implementations in user level, not by the implementation of the kernel itself. Similar concurrency. The second that you define blocking APIs within the kernel, you're defining concurrency, synchronization, all of these types of policies within the system that, in our opinion, should be at user level, or at least Composite tries to put them there and see how far we can push it. We also do very strange things like move capability, delegation, and revocation policies to user level so that we can export them out of the kernel and redefine them as appropriate. So there are a lot of different ways in which Composite tries to push the bar in different ways. To understand how we do that, you need to kind of dive into what are the abstractions provided by Composite. So I'm going to go through these relatively quickly. I think a lot of these will I don't know, feel very comfortable to people who know SEL4. They're going to sound very similar in how I initially present them, and I'll go into the differences later. So what does the kernel provide? If the kernel is meant to be minimal and we're supposed to be able to implement in components most of the required policies and functionality, what does that mean? It means that we have capability nodes, we have page table nodes. All of these are directly accessible resources from user level implemented in the kernel, and we can piece these together to create protection domains in the system. And if we combine a capability table with a page table, all of a sudden we have a component. So a component is a protection domain that includes all of the memory resources indexed by the page tables and all of the kernel objects referenced by the capability tables that define the access rights for anything executing within that component. What executes in a component? Of course, threads, right? We don't do anything to buck the historical trend since the 70s of defining threads as our abstraction for execution. What's a thread? Of course, it's a set of registers that executes in a component. We'll see that the notion of threads gets relatively complicated later. We also, of course, when we're implementing a system like this, need to understand how memory allocation works. We do not have memory allocation within the kernel. Instead, we looked at what SEL4 did with untyped memory and said that that is a fantastic, amazing idea, and just kind of ported it over. We make some significant changes to the details, but the high-level idea is the same. You can have access to untyped memory. Components can have access to untyped memory. They cannot actually do loads and stores to that memory, but it is memory that they can retype into either kernel objects or into user-level virtual address space pages. So if we're retyping, for instance, here into a thread and into a page table node, you can see that those are now referenced from within the capability table because, hey, now they are actually kernel objects that we program. As I said, we can also retype some of this memory into virtual memory and map it up into components, and therefore it's actually present and accessible to loads and stores for those components. So the retyping facilities of the kernel seek to keep the kernel safe and to keep components safe by simply providing the guarantee that no piece of memory can be typed as can be accessed as multiple types at the same time. So any piece of memory is accessed as one type and only one type within the system. And there are complicated rules for generating that, but that's how it maintains safety. We also have things like IPC in the system, of course. We have multiple components and we want to talk between them, coordinate between them. As I talked about, we want to compose them into these component hierarchies within the system. And we support both synchronous and asynchronous IPC. I'm going to go into both of these in detail because these are kind of the core of what makes Composite able to do things like user-level scheduling. Before I go into that, we need to understand a little bit about how traditionally you think about IPC within microkernels or within operating systems in general. Option one is we use things like asynchronous IPC or bounded asynchronous IPC and things like pipes, right? And that's just the idea that we could have multiple threads and they can coordinate with each other. They might have different priorities, in this case X, Y, and Z for different threads. And if we want to kind of pass messages between them and we want to essentially assess how long it takes for a message to percolate through processing throughout the system, from the thread on the left to the thread on the right, we need to do some sort of an end-to-end timing analysis that understands the dependencies throughout the system. Especially when these threads are located across various cores, this can actually lead to a fair amount of pessimism. There's a lot of active research in trying to make this better and faster. We've also noticed that, over the years, most microkernel IPC ends up being synchronous, and that ends up being for good reasons. It's a lot easier to coordinate in that way in some cases, and it can be a lot faster. It's not that, it's synchronous IPC is inherently better, but a lot of microkernels have gone in that direction for a lot of functionality. And what does that look like? Well, we typically do synchronous IPC between different threads. So again, we have these 3 threads in the system, and now instead of sending asynchronous messages, we rendezvous on some sort of an endpoint between threads. So priority, the thread in the center might await a call from the thread on the left. Once the thread on the left makes a call to say, yes, I need your service, I want to effectively invoke some sort of a function within you. Then they rendezvous, it wakes up the middle thread, etc., blocking the thread on the left. This actually bakes a lot of the concurrency logic into the kernel and the synchronization logic within the kernel. It adds a lot of assumptions for things like ordering, for things like priority into the system. So it's hard to remove policies from the system when you're doing this. If you want a predictable system, it also requires that you do things like priority inheritance, do considerations around priority ceiling, manage budgets. These are all tractable problems, but they require a lot of engineering, and they all inherently bake policy within the kernel in some sense. So what's interesting is we looked at this and we started to see that if you look at history, we see on the far left this notion of synchronous rendezvous between threads as being the primary and only way to coordinate within the system. And this was, back in 93, 95, a lot of Lika's original L4. And since then, we've been moving more and more to the right towards this notion of what's called thread migration. And this is simply the idea that you want some notion of that execution that started on the client on the left to go with the IPC, to go with the invocations as it percolates through the components. So Fiasco has Credo support, Nova has priority inheritance support. These allow some notion of the thread, the execution context, to go along with the IPC within the system. Cell 4 with MCS support doesn't allow priority to go throughout the system, but it does allow budget to go along with invocations. So a lot of these types of systems are moving over towards thread migration. Composite actually represents a system that goes all in on thread migration, and it always had. Thread migration is simply the idea that I might have multiple components in the system, and if I have a thread on the far left and it wants to make this invocation to the middle component and then to the component on the right, it actually ends up logically flowing between them. So as it makes function calls, the executable thread continues execution into the middle and then the right component. And then, of course, when the right component finishes its execution, it returns to the middle returns to the left, etc. Now, of course, done naively, this is very dangerous, right? We can't have kind of thread context just accessible across all of the components. We still want to maintain isolation between them. So this requires that you have things like the execution context for stuff like stacks and register contents and stuff like that. Existing for that thread in each component. It requires that you still have separate protection domains for each of the components, but the logical executable entity persists in its execution between different components. There's only one priority that exists for it, there's only one budget that exists for it, etc. This does mean that as multiple threads, for instance, invoke that middle component, we might need multiple execution stacks, and managing how many execution stacks, how to allocate them out at user level, all of this is relatively difficult, but you can see the publication at the bottom for how we dealt with it. One of the key insights from thread migration is simply that because we are not switching between threads as we do IPC throughout the system, it means that we don't need to ever involve a scheduler on IPC. And that enables us to be able to move the scheduling logic entirely to user level. So within the kernel, we provide dispatch, and schedulers implemented in components are able to use that facility for dispatch to actually switch between threads and define their own scheduling policy. Indeed, the kernel barely knows what a priority is. Schedulers define priorities in their user-level data structures. Run queues are in the user-level schedulers. So if a scheduler is executing in this thread and it wants to switch over to another thread, it simply needs access to a thread within its capability table, which gives it the ability to dispatch over to that other thread. This is not user-level scheduling as defined by a library in traditional systems like scheduler activations, because the threads that you're switching between, dispatching between, might be implementing in any protection domain, right? The scheduler doesn't know that. The scheduler's job is just to decide which to run at any point in time and can dispatch between them accordingly. Because the scheduler defines all of its logic for prioritizing budgets, all of that stuff, it defines its own notion of budget priority for all of these threads. So switching between threads means that it naturally can switch between not just the executable context using dispatching, but also its own notion of which thread is running and account for them separately, prioritize them separately, etc. Now, that's only part of what a scheduler does, of course, right? Yes, the scheduler decides which thread to run at any point in time. And right now, we see that it can do that in a really interesting way. But we don't actually define blocking semantics by the kernel in doing this. Instead, when a thread wants to cooperatively block, it invokes the scheduler. So we use IPC to call to the scheduler, and the scheduler provides this dispatch. But that's not all that you need to actually implement user-level scheduling. Additionally, you need a source of time. So Composite provides the ability to vector timer ticks up to these schedulers in a controlled way. The schedulers can actually define their own granularity for these timer ticks on a cycle-accurate granularity, well, depending on what the hardware can provide on x86 on a cycle-accurate granularity. But this is actually sufficient for implementing a system. But we also need to actually answer the question, what happens with other interrupts in the system, not just timer interrupts, right? And one option would be for all interrupts to be vectored to the scheduler, and that would solve a lot of problems. But it does have some performance repercussions in the system, because now the scheduler needs to be involved on the processing of every interrupt. And that's possible. We have done that in the first version of the kernel. But to avoid that overhead, we came up with a way where we could actually vector these interrupt sources up to threads that are executing in the different components, which is to say, the kernel can be told by the scheduler using a mechanism that we call temporal capabilities, whether when a networking interrupt arrives, for instance, the thread that it's destined for, the interrupt processing thread, should be run immediately, thereby preempting the currently executing thread. And we make these decisions using something that we call temporal capabilities. And I'm going to brush over these. They're a really cool abstraction, one of the abstractions I'm the proudest that we implemented in the system, and you can see the paper for that. A temporal capability is just a slice of time that has been given for execution of a thread on that TCAP, on that temporal capability, and a integer that's interpreted effectively, or a set of integers that's interpreted as a set of priorities to decide whether preemption should be made. And the way that the scheduler maintains control in the system is that it is in complete control of programming these time slices that are allowed for execution and the priorities. But TCAPs are also interesting because they allow us to implement multiple schedulers in the system. Because schedulers are defined at user level, we might want to have multiple of them so that we can specialize different parts of the system for different goals, performance, predictability, etc., right? And TCAPs allow different schedulers to delegate slices of time to each other, thereby passing the temporal resources throughout the system so that the execution can be done in these different schedulers using that time. So this is interesting because it allows us to create a hierarchy of schedulers, or even a full graph of schedulers that are all coordinating by passing time. TCAPs are a very difficult abstraction because they want to allow these schedulers to coordinate while necessarily constraining their impact on each other. A scheduler wants to say, hey, I'm going to give you some time, you other scheduler, but I want to guarantee that you will not use that time to interfere with this set of threads that I want to be able to execute at the highest of priorities. So this is one of the resources I didn't go over before that we have in the system. And if we think about now the kernel objects, we have threads, temporal capabilities, synchronous endpoints that enabled us to connect these resources and allow thread migration between them, asynchronous IPC, that's effectively that notion of interrupts being able to generate execution. And of course, we generalize that to asynchronous communication between threads, and registers and threads that you see at the bottom here. So the one thing that I want to point out here is that every thread now maintains an invocation stack that tracks the sequence of the different components that that thread has executed between as it invokes the interfaces for each of those components. And of course, we can return from a component. It pops an entry off just like a normal C execution stack. But of course, because this is a kernel resource, it's trusted and cannot be corrupted in any way, shape, or form. Now, this raises a number of questions, right? It's nice that we have this facility for defining scheduling policy at user level, and it's allowed us to do a lot of research into providing these different domains of goals within the composite infrastructure. But there's just this intuitive notion that doing user-level scheduling is probably too slow, right? So we have to answer this question of essentially, is it fast enough to be able to do what we need in the system, right? Does it slow down scheduling to the point where it's useless or it limits the system in a significant way? Well, we've gone through about 5 iterations of these user-level scheduling infrastructures through 3 versions of the kernel, and we've ended at a system with Slight that Fani did a couple of years ago that actually allows user-level dispatching of threads to be on the order of 41 cycles. So when we're doing cooperative switches, we actually have dispatch on the level of kind of thread-based user-level scheduling libraries. When we're doing preemptive scheduling, then we need to dispatch from the kernel, but that's on the order of 300 cycles. In the end, this notion of the scheduler being defined at user level, it's not that prohibitive. The policy ends up looking relatively similar to what it would be in the kernel, a little bit simpler because it's at user level, and the dispatching latency is not an inhibitor. But there is another source of concern here, because now if we want to do cooperative switches within the system, we don't have a blocking abstraction within the kernel, so we need to invoke the scheduler asking for ourselves to be blocked. So is IPC too slow if it's on the path of a lot of these scheduling decisions? And IPC, it's hard to look at cycle counts on their own and get much from them. So I add a comparison to SEL4 here, because SEL4 is one of the faster IPC systems in the world now. I'd say it's probably Nova is maybe the only other system that I know of that is highly competitive with it. And if we look at x86-32 and Cortex-A9, you see that for a round trip IPC from client to server and back on SEL4 and Composite is competitive, if not better here. So IPC is not free, but it ends up, in our observations, not being prohibitive, and our scheduling latencies end up usually being significantly faster than those in Linux. So in systems where Linux is sufficient, you'd expect this to be sufficient as well. In systems where Linux isn't sufficient, like some of the real-time domains, then we have to kind of go into kind of a design mode and make sure that everything is as efficient as it can be. So this is one core aspect of how we think about system design in Composite. We want to enable this notion of user-level policies defined by components. That means removing the policies for things like concurrency from the kernel. And that means using things like thread migration. So we've made it practical in many different ways and have demonstrated the ability of user-level scheduling to do pretty significant to have pretty significant benefits. An additional area where we have tried to essentially remove implicit policy from the kernel is that around scalability bottlenecks as we increase the number of cores within the system. The big question here is, can the kernel's APIs and implementation in some sense limit the scalability of components or cause interference between components? If the kernel's implementation of its own primitives limits the scalability of the system in some way, then it is imposing performance policy on those components. Our goal is to essentially say that if your user-level code executing in a component is scalable, it can do well as you increase the number of cores, we want it to actually be scalable, which is to say that the kernel gets out of its way. So we take this very strong version of, we really want to move the kernel out of the way and define policies in user level. And that includes actually not putting prohibitive overheads for things like scalability. And this is difficult because on the bottom left, you see we have a component that is coordinating in itself across different cores. And as it makes system calls, the arrows going down and up, if we have, for example, a big kernel lock that interposes on kernel operations to prevent race conditions, then we're no longer kind of achieving this goal, right? That one lock on its own means that the kernel is going to be inhibiting the scalability of that user level process. In the center diagram, you can see that there's one component that is trying to coordinate through the kernel, let's say using message passing APIs across cores to another component. And again, this notion of it making those calls and, for instance, requiring a big kernel lock means that another component executing on that destination core might actually feel the negative performance and predictability impacts of that message passing. And the worst case is on the right, whereby we have two components that are completely isolated from each other, executing on different cores, but they inhibit each other's execution simply because they make system calls and there's a big kernel lock that prevents the performance properties of the other core. The other core has some performance impact on the component on that other core. So these are a few of the cases that I motivate here, and the exact same thing actually applies for IPIs. When we think about coordinating between different cores, we think, yes, shared memory is one way to do that. Locks are a way to mediate that. IPIs are another, right? If you have a multi-kernel based system where you share no memory in the kernel, then this locking concern is not really a concern. However, you often do use things like IPIs to, in event-triggered way, coordinate between the different cores. And I want to focus in on the middle case here, where we have a component that's sending a message to a component on another core, which is causing IPIs onto that other core. But the IPIs might cause execution that interferes with the other component that's executing on that core. So again, this is policy imposed by the kernel mechanisms within the system that place limits on what you can actually define in user level in terms of performance. The same could exist on the far right in an even worse scenario where, for instance, we need to do TLB shoot downs, scheduler run queue rebalancing, stuff like that, where two components, again, that don't interact with each other and should be otherwise isolated can feel each other's performance impact by these IPIs. So we really want to avoid all of these things, and Composite takes a very aggressive tone for this and essentially says that to solve these problems, the kernel must be entirely weight-free, and that components at user level should entirely be able to control cache line contention within the kernel, which is to say that policies should be able to be defined whereby two components should be completely guaranteed to never write to a shared cache line within the kernel, therefore should never cause a performance impact on each other with respect to an increasing number of cores. So this means that the kernel can have no locks. This means that the kernel, by and large, can't really have reference counts. This means that we need to take a very aggressive stance to the implementation of the kernel. So we do this by integrating a scalable memory reclamation facility based on time in a library that we've called Parsec. And you can read about it in the spec paper. I'm not going to go into it, but it and a few other facilities are what's required for actually implementing this. So this has allowed us to scale up across many different cores in a pretty successful way. And we additionally provide facilities for enabling components to define effectively every single time that IPIs are used throughout the system. The kernel itself does not use IPIs for any of its mechanisms, and instead user level policies are defined for controlling that when IPIs are actually used. Again, we want the kernel to get out of the way so that user level can have maximum flexibility. So we've looked at using composite in a lot of different domains. And I just want to go through a few very quick examples here where we look at embedded systems on the left, small little microcontrollers in the middle, and edge data centers on the right. On the far left, we have a lot of work that we've done here, and I'm just going to overview some of it, mainly from an engineering standpoint. We've implemented a principle of least privilege focused RTOS on the system. We've also implemented a personality for that same RTOS on SEL4 and compared the two. We've implemented NetBSD rump kernels on the system, Zen-like driver domains, and coordinated time coordination between them. We've ported the NASA's core flight system to be able to do flight control within the system, mixed criticality systems, and we've implemented ways in which you can have different systems, some that are mission critical on the embedded system, and some that might just be there for convenience, these mixed criticality systems, and defined ways to coordinate between them so that the less important software on the system can't really interfere with the more important stuff on the system. I'm not going to go into that in much detail, but I do want to dive into this interesting facet, which is microcontrollers. And microcontrollers are not a place that you typically think a microkernel would be or a component-based system would be, because these have 128, 16 to 128 kilobytes of SRAM. And they don't even have MPUs. They don't have virtual memory. They don't have MMUs, they don't have virtual memory. Instead, they have memory protection units that just allow you to open windows to physical memory that are accessible or not. So we've actually implemented a paravirtualization infrastructure, a microcontroller virtual machine infrastructure on the system in which we, in which we can run multiple FreeRTOSs on the system, or generally multiple RTOSs. And we had to overcome a lot of challenges with this that required us both to modify the kernel and to be able to modify a lot of those user-level components specialized for this kind of low memory, performance-sensitive type system. And just a very high-level overview of this, we looked at how an MPU-based isolation versus page table-based software isolation how we could span the gap between these. And we used path-compressed radix trees to flatten a system of protection into the required limited MPU regions. And because we have these limited MPU regions, we came up with different techniques, some static, being able to solve for memory layouts so that we could fit all of the required protection into the required memory, the limited MPU regions. But then we also treated these MPU regions as a cache and allowed as what looks like essentially a software managed TLB, so that we could have an infinite number of protected regions for a component, even though we have a finite number of MPU regions. And more recent work enables us to have efficient coordination with devices by doing kernel bypass around interrupts. And I'm not going to go into that, but it's pretty cool. So this allowed us to run, up to 8 virtual machines and 128 kilobytes of SRAM with this system. And I'm not going to go into the details here. You can look at the papers or you can pause. But the whole idea here is that there are some performance impacts for doing this. But by and large, the microkernel VM is not that much slower than raw FreeRTOS executing with no isolation whatsoever. So this means that you can have strong isolation in these small microcontrollers without giving up too much in terms of performance. And we've actually taken it down so that interrupts can actually have bare metal interrupts latencies in work that uses trust zone M. So we've also, on the complete other end of the spectrum, looked at these relatively large systems that are focused on the edge. And we look at these as being essentially kind of our traditional data centers, requiring multi-tenancy, requiring performance, all of that, but shrunk down to much smaller facilities that could fit into a network edge, right? That might be a set of racks, that might be a closet worth of information, that might just be a couple of servers. So density becomes very important. We have many tenants and they all need to fit onto the system. But then additionally, things like 5G provide 1 millisecond round trip latencies. So we really want to be able to have the software infrastructure of the system, in spite of this density, have very strong latency properties. So we looked at what we might be able to do to implement this type of a system. And if we use processes, well, processes don't provide that much isolation because of full Unix-based APIs. They are relatively scalable. We can get good density with them. them. And they provide decent startup time. The thing is, we want to be able to provide isolation for each client within the system. So we require the creation of new protection domains for every client coming in. So startup time becomes really important. You see these types of constraints a lot in serverless computing. And high-performance networking is relatively, you can't really use DPDK and scale up to high density because of the isolation requirements. So high-performance networking, you're kind of stuck with what Linux gives you, which is very fast, but maybe not as fast as if you were using bypass. Containers and VMs, on the other hand, provide stronger isolation, but are not as scalable, have bad startup time, right? So we've implemented a system called EdgeOS within Composite that provides an abstraction for featherweight processes that attempts to provide all of these functionalities. And the goal is that we can provide 10 to 100 gigabits per second processing of packets without sacrificing isolation. Every client that tries to connect to the system should be completely isolated in its own separate protection domains. We want the startup of these different clients' computations to be very, very fast, and we want it to scale up to thousands of these computations per host. So this is a high-level diagram of what we've done. In Composite, we've implemented components that provide things like DPDK for network access, something that controls the FWPs, the manager for them, to create them very quickly, to recycle them very quickly. And FWPs, these featherweight processes, can be added into chains of computations. If you're familiar with network function virtualization, that might sound familiar. And then our scheduler is optimized for being able to deal with the high density and fast activation and controlled latency, and all this is implemented on top of Composite. And what we can see here is that if we look at the startup time of these different technologies, that if we look even at just fork and exec within Linux, right? EdgeOS allows FWPs, because it's so optimized how we create these things, to be about 20 times faster. With our checkpointing and restore support, we can actually activate these even faster in response to new client requests coming in. So responding to a client request in 6.2 microseconds is around the level that we want to be at for these types of high-density systems. And because these are so specialized, we support higher throughput than Linux for things like TLS endpointing or proxies. And all of this is despite EdgeOS using message passing throughout this entire thing. We provide no shared memory between the different FWPs. So it's very, very strong security within the system. So I've talked about the system scaling all the way down to microcontrollers, and now I've talked about the system that's relatively large on the edge, focused on security, density, multi-tenancy, and performance. And you can start to see how this component-based design can actually span the gamut between all of these different systems and hopefully satisfy a lot of future research and hopefully a future foundation for different systems. So if you have any questions or comments, please ask. This is all open source software, so you can find it all, and you can find all the papers on my webpage. I will be looking for new PhD students, probably in about a year. So if you're interested in looking at this work, send me an email. Let me know that you saw this presentation, and we can chat. Thank you so much. I really appreciate it.